Draw a Lewis structure for XeOF4. So Lewis for XeOF4. So this is where it gets a little bit tricky because xenon is actually a noble gas. It has no reason to even, or at least a noble element. It has no reason to even make these bonds. It really doesn't serve that purpose because it's a filled octet already. It has 8 electrons. But nonetheless, nature is imperfect. Things do bond that don't really make sense. As long as other rules are satisfied, it gets a pass. With that being said, xenon can contribute 8 electrons from that. Oxygen, 6 electrons. Fluorine, there is 4 of them. So although it's 7 electrons, it's 7 for each of them. So that's 28 in total. So in total for all of this, we have 8 plus 6 plus 28. We need to account for 42 electrons, which sounds daunting, but I know we can do it. So we have xenon in the center, okay? And now, right away, we're really just going to break this octet. We're going to have it as 1, 2, 3. Let me start like this actually. 1, 2, 3, 4, 5. There we go. A little bit more spread out. That's good. All right. And now we have OF4. So we're going to have O, F, 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 F. Okay. So that part is done. Now, fluorine is currently sharing one of its 7 electrons. So we're actually going to fill out this octet first. It's the easiest one so far. 3, 4, 5, 6. Well, that's 6 of the 7, so we're good. And the same thing here. 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. And 2, 3, 4, 5, 6, 7. So we're done with that part. Now, oxygen right now is sharing one of its 6. So it's going to be 2, 3, 4, 5, 6. Xenon right now is sharing 5 of its 8. So we're going to have 6, 7, and 8. So right now we have 2, okay, unpaired electrons, one on the oxygen, one on the xenon. So what's actually going to happen here to satisfy this part, we're actually going to throw them into an extra bond with the oxygen and xenon. So actually what we have for this is going to be now, if we redrew it, okay, we're going to split it perfectly into 6, 3, 5, 6. Give it a little bit more space for the lone pair. We actually now have oxygen double bonded, but every other fluorine is still single bonded. And yes, we still have that lone pair on the xenon. So not only does it break the octet rule, I would say it completely smashes it. This is nothing close to an octet rule. So with that being said, let's fill out the octet rule for the other ones, the fluorines. So it's funny how xenon just completely ignores it, but the fluorines and the oxygens around it still obey this octet rule. And to make sure we just drew this the most stable as we can, we're actually going to compare the formal charges for each one. So as we said, oxygen's formal charge is where it has, or at least where it has a net of 0. It's when it has 2 bonds and 2 lone pairs, which is what it has. The double bond does count as 2. And fluorine is when it has 1 lone pair, 1 bond and 3 lone pairs. So that's good as well. And now xenon's a little bit tricky. Xenon for neutral is just has where it has 4 lone pairs. But we can actually expand this further to where we can actually say, based on the lone pairs, we're not replacing them per se with a whole bond, but we're actually making each one a bond. So we have 1, 2, 3, 4, 5, 6. Because the double bond counts as 2, that's 6 bonds and 2 lone pairs. Well, sorry, 6 bonds and 1 lone pair, which is actually what it has here. So we can actually still argue this has a formal charge of 0 throughout. So this would be indeed the Lewis structure for xenon oxygen tetrafluoride. Okay? So now let's see what it says here. Determine if the central xenon atom obeys the octet rule. No, it does not. Okay? Does it have an incomplete octet? If anything, no. This goes way beyond it, which is why we actually use the term expanded octet for the xenon. That is definitely what it's doing. Okay? Now it says identify the number of lone pairs, single bonds, and double bonds on the central xenon atom. So for this, we have one lone pair. Okay, we also have, for single bonds, we have 4 single bonds. And we have 1 double bond. That would be for xenon. Hopefully we cover everything for this question. But as you can see, this is an extremely expanded octet. And it's only because xenon, it's already a noble atom, so it really just shouldn't be bonding. So when it does, you kind of just throw the rule book out the window, at least for the xenon. The things surrounding it still want to follow the rule book, but xenon itself, that one's a little bit tricky. So the Lewis structure, as we saw here, perfect. 4 single bonds, 1 double bond, and 1 lone pair. 42 electrons. We didn't even count that, but let's see how many bonds are there in total. 1, 2, 3, 4, 5, 6. Because the double bond is 2 electrons each, so 6 times. So that's 12 electrons. And then we're gonna count up the outside lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times 2, that's 28. And then xenon also has 2 there. Almost missed that, so it's actually 12 plus 30, which is 42. So perfect. We do have the right amount of electrons. So let's see. It is an expanded octet, so that's perfect. Okay. And let's see. We have, where does it say it? 1 lone pair and 6 bonding pairs, of which 4 pairs are shared in 4 single bonds, while the remaining 2 are double bonds shared with the oxygen atom. So with that being said, this is correct. And hopefully you can see how xenon really just expanded completely with the octet. So let's move on to question number 7.